In this video lecture, we're going to talk about C++'s exception handling mechanism. Good places to look for notes are in the Scott text in section 8.5 and also in my notes that are called exception handling in Java, but they also cover the notes for C++. So if you may recall from the C lecture, we said at the end of it that we wanted to be able to group our exception handling code into one part of our program and our normal handling in another place. And the way that's done in C++ is with something called a try-catch clause. So your normal code executes in the try block. And if it raises an exception, it can be caught by one of a list of catch clauses. And each catch clause has a single formal parameter denoting the type of exception object that it catches. So in this case, I'm saying that the first type of exception I catch is a division by zero exception. The second type is an arithmetic exception. And then you'll notice that there's this ellipses, this three dots, and that says that it catches any kind of exception whatsoever. So it's like the object superclass in Java, except that C++ has no such overarching superclass. Therefore, they introduced it's called the ellipses operator in order to catch any arbitrary exception. You'll also notice that I have passed the formal parameter by reference, and the reason for that will become apparent later in this lecture. Just for the time being, note that we do pass it by reference. It is also possible, if you're not going to use that object, to simply list the type of the exception so that C++ can match the exception thrown to the exception that it is catching. So, what are the matching paradigms? So first of all, the parameter that you can use for that formal parameter can be a base type like an int or a string, but that's pretty rare because when you do that, you're really not giving it an exception type. So much more common is to provide a user-defined exception class. And as you'll see at the end of this lecture, there is an exception class defined by the standard template library, but there's no need to make your class subclass this exception class. As you'll see when we get to the examples, it can be any class that you want. And one advantage of using classes, in addition to making it easier for someone looking at your code to identify the type of exception that's being thrown, is it allows you to pass multiple parameters, because we're going to see that it's possible to throw an exception out of a function. That is, the function does not have to handle the exception. Instead, it can be handled in a calling function. And in this case, we may want to pass that calling function some parameter information so that it's able to handle contextually the information, because the throw could be from any number of calling functions, so it may need some information on where the throw came from. So by putting instance variables into our classes, we can make them store multiple pieces of information. Now, one important thing that catches a lot of people when they first start using C++'s mechanism is that any variable declared within the try block is deallocated before the catch statement is executed. So for example, if I went back here and I had, say, try int I equals 10, and then inside my catch I tried to print out I, this would be a compile error. The compiler would tell me that I was undefined. So if I'm going to use I would have to declare it outside the try block. Now it would be accessible to me within my catch clauses. When you actually want to go and throw an exception, the way you do it is with the throw keyword, and typically you provide an expression which is going to be an object. So the return value of that expression typically is an object. It could be, though, a primitive type like an integer or a string. So here we have an example, throw new bad operator exception, and you see we're passing the operator token and a message describing the error as arguments to it. Now typically you do not allocate an object off of the heap, but instead you throw stack allocated objects, and again we'll get to that, why you do that, in a few minutes. So the throw typically is throwing some stack allocated object. You'll see that in some circumstances we don't provide an object. It's when we rethrow an exception after handling it in a catchphrase, and we will get to that. In fact, we will do that right now. So a throw without an operand can only appear in a catch clause. It cannot occur in a try block. So the catch clause, after handling the exception, can re-raise it and propagate it to a calling function. Now, you cannot propagate it to another catch statement in this same list. So if we go back to our initial example, we have a try, and let's say that we had a throw here where we throw division by 0 exception, and we catch it here, and let's say after printing out I we rethrow it. It would not get caught by the arithmetic exception handler, even if the arithmetic exception is a superclass of the division by 0 exception. We'll see momentarily that when we do this formal parameter matching, supertypes will match a thrown exception. So only one catch clause can handle an exception in a list, and that will be the first catch clause whose formal parameter matches the exception. If there is a rethrow, as there is in this case, it will go to an enclosing try block. The next question is how exceptions get matched. And as you've already seen, the formal parameter is what C++ uses to match exceptions. So it will explicitly match exact formal parameters. So if I throw an object of type T and my catch clause has a formal parameter of type T, then it will match them. Similarly, it's often the case that you'll put const T in the catch clause because you want the compiler to be able to do optimizations based on the fact that you're not modifying the formal parameter. That works. Also, anything that's a reference parameter will match, or a constant reference to a formal parameter. In addition, any supertype will match T. So if T is a derived subclass of some base class S, and S is our formal parameter, then S will match T. So going back to our example at the beginning, if arithmetic exception were a superclass of division by 0 exception, and I did not have this catch clause here, so let's say it was not here, now the division by 0 exception would be caught by arithmetic exception. In effect, arithmetic exception is an upper bound on the exceptions that can be caught by this particular catchphrase. So here's some more examples with catching different exceptions. We have a class called exception and a class stack exception extending exception. So it's a subclass of exception, and we throw stack exception out of a try block. So each of these four statements will catch it. So the first two are formal parameters exactly matching stack exception, with the second one being a reference parameter. The second two are superclasses of stack exception, namely exception, and you see that either a stack allocated object of E or a reference parameter E will catch it. Now, importantly, what will not be caught is pointers to these objects. So if I have a catchphrase that says the formal parameter is a pointer to a stack exception, then that catch statement will not match this thrown stack exception because the parameter down here is expecting a pointer to a stack exception, not a stack allocated one. So, a few considerations when you throw objects. First of all, it's considered to be a bad idea to allocate objects off the heap. So you don't want to say down here, you would not want to say throw new stack exception. And the reason for that is that means that some catch clause farther up the chain that catches it is going to have to deallocate the object. And if it forgets to do so, that's a memory leak. You don't want to make your catch clauses have to worry about when it's right to deallocate the object. So, good practice is to throw your objects off the stack. Okay? Now, the other thing is that sometimes if you rethrow an object, you will have modified it and you want its modified contents to be thrown. That is why we use the reference parameter. If we use a reference parameter to catch a thrown exception and we modify it as we do here and then rethrow it, that modification will be included in the rethrow. By contrast, if we declare the formal parameter as a simple stack allocated object, then the change we make will not be reflected in the rethrown object. What happens is that C will throw a copy of the original passed in parameters. It's just mimicking call by value semantics in C. If you want to change something, you use a reference parameter. If you don't want to change something, you use a call by value parameter. Also, as we've just mentioned, the throw is matched by examining the catch statements in sequential order, and it means that you want to place the more restrictive types before the more general types. Okay, so again, going back to our example here, if we had put the arithmetic exception before the division exception, then the division exception could never be gotten to if it is a subclass of arithmetic exception, because the arithmetic exception will always catch the division by zero exception. So you always go from more restrictive, which is division by zero, to more restrictive, which in this case is the arithmetic exception, to the least restrictive, which is the universal catch. And then also, if none of the catch clauses match, then the throw is propagated up the call chain to an enclosing try block. In fact, if there were an enclosing try block locally, that try block would be first tried. So basically, we propagate the exception up to the next enclosing try block if it is not matched by one of the catch clauses for the local try block. If a handler catches it, then execution picks up following the try construct. It's the first statement following the try construct. So execution will not return to the statement after the throw. So if we, again, going back up to our example, if we do the throw right here, and let's say that after that we had I equals I plus 20, the I equals I plus 20 would never get executed because the catch statement right here would actually catch it. Let's say that the throw is not here. An execution would then pick up here. Let's say that we printed out I right here. What would print out is the value 10, because that is the value assigned to I here. So again, once you throw, you can never go back into that try block, at least if you're not part of a loop. If you're part of a loop, you could re-enter it. But the idea is that once the catch clause has finished execution, control picks up with the first statement following the try block, or following, in fact, the list of catch statements. Another important characteristic of C++'s try-catch mechanism is that throws up the call chain are structured. So if I have a series of functions, let's say I had main, which had called A, which called B, and that called C. And let's say that we had the try in A, in main. It called A. And ultimately, our throw of something, we'll say throw foo, occurred in function C. But let's say that it's caught in main. What happens is the stack frames for C, B, and A are all popped off the stack, and any stack allocated variables that they may have declared, such as parameters or locals, are deallocated, and if necessary, destructors are called on them. Contrast this with long jump from set jump long jump from our C lecture, where the stack frames were in effect just completely, they were popped but also ignored when the long jump restored the register contents to what they had been at the initial set jump. And the issue with that is, if you recall, is that variables could be left in registers and not written back to memory. That does not happen with C++ because of the structured popping of stack frames. So any variables that were in registers will be written to memory. There's no loss of values. Finally, C++ does have a predefined exception object that it defines in the standard template library. It is called exception, and you include it in your program with include exception. It has a single method called what that returns a char star string representing the type of exception. So the default implementation just returns the string std : exception. But you're free to override the what method to return a more descriptive error message. Now, in addition to exception, the standard template library has another number of useful subclasses. The most useful ones I have listed here. So there's one called bad alloc, which is raised when there's some problem with the new operator. So basically, if new fails for any reason, like you tried to allocate a negative amount of memory, there wasn't enough memory, you get a bad alloc exception. If a dynamic cast fails, so if you may remember, you can do dynamic casting using the dynamic cast operator. So that is dynamic cast. Say if I wanted to convert a double, and let's say for some reason I gave it some value like say foo, which is a string that could not be converted. That would get a bad cast exception thrown. Then we have logic error exception that's basically used by classes in the standard template library. So the out of range exception is thrown by things like vectors, queues, and dequeues if you try to use a subscript that's out of range. The length error occurs when you try to resize certain elements like strings or vectors. They may raise this error if the operation fails. Finally, we have runtime errors. The one that's quite useful was just introduced by the C11 standard. It's called system error, and it will allow certain OS generated errors to be trapped by your program or handled by your program. Now this is platform dependent, and the way it's done is that the C++ converts an error code given it by the operating system, and that error code will identify the type of error that has occurred. Now, this error code is system dependent and not portable, so you'd have to look up what those error codes mean on whatever platform. This makes it a bit dicey to use simply because you will not be able to have your code be universally compilable and portable. That concludes this video lecture on C++'s exception handling mechanism. In a separate lecture, I'm going over a specific concrete example with so-called safe arrays that shows how exception handling can be applied to a real-world example.